So looking at page 5, we're talking about Riemann sums. Before we get into the full-blown Riemann sums, we're going to talk about rectangular approximation over finite subintervals. Right? So that's kind of where we're living at this point. This page really just kind of gets into the process, but I'm going to walk you through that in the next page or so. All right. So let's jump on over to example 1 on page 6. It says find the upper and lower sums for the region bounded by the graph of y equals x squared, or f of x equals x squared, and the x-axis between 0 and 2 for n equals 4. Right? So n is representing the number of subintervals that we're going to be using as a way of breaking up the area. All right? So let me draw that parabola over the appropriate interval. Alright, so f of x equals x squared. Alright, so what I want to be doing here is, again, breaking this up. First off, restricting it between 0 and 2, so let's start with that. I'll put 2 over here. Now, because it's y equals x squared, we know that 2 is going to correspond to a y value of 4. So we'll keep that in mind. All right. So I want to break this up into 4 equivalent subintervals. So slice it or split it down the middle. I get a 1, I get a half, and I get 3 halves. All right. So that would make my 4 subintervals. Now, when they say find delta x is referring to the change in x related to each of those subintervals. Right? So each one of these represents a delta x. If I can draw, I can. All right. So what we would want is a shorter or quicker way to figure that out. Well, if we take the length of the interval and divide it by the number of subintervals, that'll give us the length of each subinterval. So 2 minus 0 divided by 4. Now, when we typically define a domain for a function, we would normally say something along the lines of f of x if x exists over the interval of a to b. Right, so in this case we're saying f of x is equal to x squared if we're looking at the interval of 0 to 2. Right, so that's defining the 0 and the 2 as b and a. Right, and we already know based off of the way the example was phrased that the 4 is the n, so we now have a general rule. We could say b minus a divided by n is going to be equal to delta x. Alright, so now what we want to do is figure out a way to come up with the areas bounded by the curve and the x-axis for each one of these subintervals. Alright, so you can see here that we have a choice of working left to right or right to left. So it begs the question, well, how does one go about doing that? Well, a good diagram anyway, goes a long way. Alright, so what I'm going to do is I'm going to duplicate this. I'm going to bring it down a little bit. I'm going to copy and paste. Alright, oh, kind of schmidge it up there a little bit. Alright, so I'm going to draw some rectangles such that the upper left-hand corner of the rectangle is on the curve. All right. Now, in this case, I'm getting a rectangle with no height, but it's still, we're still going to call it a rectangle. All right. Upper left-hand corner of that rectangle is on the curve. Just doing a quick rough sketch here. It's not pretty, but it gets the job done. Now, if I were to find the area of each one of these rectangles, I would have an approximation of the area under the curve, but I wouldn't say it would be a good one, right? Because there's a lot of area that I'm missing. I'm not getting any of this, right? All of this is being excluded, right? And I want all that if I can help it, right? So maybe we tried coming in from the right. So starting on the right hand side, we draw rectangles so that the upper right vertex is on the curve. All right, so I think we're getting into kind of Goldilocks territory here, where this one's an overestimate, and this is going to overshoot the area. You're going to get too much. The other one's going to get too little. We want one that's going to get us just the right amount. All right, so, well, at a minimum, we'll have an idea of, where the true area lives. It's going to be somewhere between the area that we would get by adding up all the areas of the blue rectangles and all the areas of the pinkish, hot pink, I'm not sure what color that is, rectangles. All right, so at least we'll kind of have narrowed down the field a little bit. All right, so if you look at the table, well, kind of table, it says values on the x-axis used to find the areas, or rectangle areas. We call that lowercase m sub I. All right, I'm only calling it lowercase m sub I because I need to distinguish it from the other values in my second diagram. So one of them's lowercase, the other is uppercase. It just so happens that this is going to be the underestimate, the one that's going to short us the area, and the other one's going to overshoot the area, but it really doesn't matter. All right, so the values on the x-axis that correspond with the points that give us the rectangle height. All right, so those values here are 0, a half, 1, and 3/2. Now it says in the next step here, plug each x into f of x. All right, well, f of x, I'll just make a note here, f of x is equal to x squared. That's just telling us to take each of these values and square them. Easy enough. 0, quarter. I say easy enough, watch me screw it up. 1, 9/4. All right, so it kind of begs the question, all right, cool, why do we do that? Well, that would give us the actual height of the rectangle, because if we evaluate the function at that particular x value, that's going to give us a point on the curve. All right, so what this just told us is that we have a point here at 0, 0. This one is 1/2, 1/4, 1, 1. 3/2, 3/4, 3/2, 9/4. And this one, well, that last one's irrelevant. All right. We're going to get a lot of overlap when we go from right to left, but that's okay. All right, to be expected. So what that's telling us is the height, again, of each of these rectangles. So I know this first rectangle has a height of 0. The second one has a height of 1/4. Third one has a height of 1, and the last one has a height of 9/4. The next step in the process tells us to multiply the values above these values by a half. So 0, 1/8, 1/2, 9/8. All right, so then it begs the question again, well, why 1/2? Well, we know that each one of these subintervals has a length of delta x, but specifically, I mean, we didn't do the math, but 2 minus 0 over 4 is equal to 1/2. It was kind of intuitive because we created the graph, and each interval was half a unit away from each previous interval, or marking for an interval anyway. All right, so we're looking at a length here of 1/2, 1/2, 1/2, and 1/2. All right, so if I want the area of a rectangle, then what I would need to do is multiply the length times the width. So 0 times 1/2, 0. 1/4 times 1/2, 1/8. 1 times 1/2, 1/2. And 9/4 times 1/2 is 9/8. Okay, so we got that. So that's good to go. Then we just add these four numbers together. All right, so I'll just do a little copy job here. Oops. I missed the Mac. So add these up. Now we're finding sums here, so you kind of can already see how this is going to connect with that summation stuff we were talking about. But we can just do a quick. It's only 4 values, so nothing too crazy, nothing too fancy. So you get 1.75 on the low end. All right, so now we're just gonna do all that again, just from right to left. It's gonna be a lot easier this time. All right. The values on the x-axis used to find the rectangle areas. We're ignoring the one on the y-axis. We're looking at this one, which we know is 1/2, 1/4. This one, which is 1/1. 3/2. 3/2. Geez, yeah, that's how you write 3/2. 3/2, 9/4, and 2/4. They only ask for the x value, so I'll just jot those down. So 1/2, 1, 3/2, and 2. Plug each into f of x, already done. So 1/4, 1, 9/4, 4, multiplied by delta x, 1/8, because delta x is 1/2, so 1/4 times 1/2 is 1/8. 1/2, 9/8, and 2. And then add them together. Oop, locked up on me. Just froze for a hot second there. So if you look at this and compare it to what we computed previously, instead of 0 plus 1/2 plus plus 1/8 plus 1/2 plus 9/8, we're dropping off the 0 and tacking on a 2. This is just going to give us 3.75. So what we now know is that our final area, that area bounded between the curve and the x-axis, has to be somewhere in between 1.75 and 3.75. Smack dab in the middle? Well, if it was a linear function, I would be confident in saying yes. It's not, so I'm not confident in saying yes. It could be, but I'm not willing to take that